your deposition. This is the optical performance for this full cavity structure. This is the reflectivity measurements from the full cavity structure showing a cavity modes, leaking cavity modes, which is showing a good quality of vertical cavity structure. In the right hand side image we see a photoluminescence results from only active region, which has a Q factor of 20. This is without distributed Bragg reflectors. This is half cavity, it is only the bottom dielectric DBR. When we complete the full cavity, we increase the quality factors of 500, which is showing the good quality in these layers. If we summarize this section, we say that all dielectric DBRs, all means bottom and top dielectric distributed Bragg reflector vertical cavity, we can say that we reach high quality of yin and active regions, since this yellow has defect-free gallium nitride substrate. Also, we integrate the dielectric bottom dielectric DBRs for the into the vertical cavity structures, which helps us to eliminate the need for the substrate removal. For the last words, I can say that my investigations are mostly related to blue optoelectronic devices like LEDs and vertical cavity structures, and I investigated active regions which I used in these optoelectronic devices, and we see that we can mitigate the efficiency loss problem and implement this into these light emitting applications. Thank you very much for attending my presentation. If any question comes.
So what is the dependence of the lattice mismatch which depends on the indium content, where you show this in the multiple quantum well structure, for example?
You say dependence of lattice mismatch, indium nitride and gallium nitride, right?
Indium gallium nitride.
The problems, 430 nanometer, this 15% indium composition is now good quality, which has lower density of dislocations. However, when we increase to 30%, the problem starts, and the indium clustering starts in the active regions, which has deteriorating the quality and optical quality especially. So for that reason, we just stick 15% indium composition, and we always shoot there to improve the active region quality. I mean, for the lattice mismatch, indium nitride and gallium nitride has specific in-plane lattice constants, so the technology is developed in that way, so we can efficiently use 15% indium nitride.
Because I assume if you make the quantum well thinner, the lattice mismatch should play more role in the. It might create surface states in the interface states.
That might be, but however, the thicknesses we use, we don't see those problems. So we use different thick layers, like in 2 nanometer, 1.5 nanometer wells. So when we use 15% in our MOC, we always get what we wanted.
So how can you make sure that you don't create super lattice instead of multiple quantum well there? Because the confinement is so high if you make the quantum well thinner, right?
Yes.
So
what we do is...
So there should be intertunneling between the neighboring, the adjacent, right?
Yeah.
Quantum wells, so you end up with super lattice.
The electron and hole wave function over there. So it is gonna, of course, it depends on the quantum well Also, quantum barrier, how thick we use. We use 12 nanometer thick quantum barriers, or 3 nanometer quantum barriers. It is also, we changed the composition of these barriers, and we found that 6% quantum barriers with 3 nanometer thick was the best design for higher light output. This was the goal. So that is what we get.
But it's amazing to have bound states
Yeah.
for 3 nanometer, 2 nanometer thin quantum well, right?
Yes,
I mean,
exactly.
I expect some leakages, right, for upper levels.
That might be true. However, for the efficiency loss, those all are combining into. Those are all in the picture, you know. So, however, we just specifically select. This is our problem. We wanted to eliminate that problem. For that reason, we use algan barriers or staircase electron injectors. So. That there might be another problems. However, which one you focus, that's the important, right? So that's what we do. We just select our problem and shoot it. That's it.
Thank you.
Welcome. I hope we can fix this problem.
Can I ask another question? How do you mean by semipolar? I mean, how is this polar? Is it the surface polarity due to the surface states, empty and filled states of?
This is the.
Or is it something different? Because I never heard the term semipolar for surface states. It's either polar or non-polar surface, right?
Yes. However, depends on the growth method. You can obtain semipolar surfaces too. So, for example, what we use, in order to obtain non-polar gallium nitride, we use silicon 111 substrate. In order to obtain semipolar gallium nitride, we use silicon 001 substrate. That might be vice versa, but we can check. As I shown before, it is how you etch this substrate, so you can obtain different surfaces, some semipolar surfaces. So it might be 11 bar 01 or 112 bar 2. For example, we also used M-plane sapphire substrate. When you just directly grow on M-plane sapphire, I might be wrong. Yeah, it is M-plane sapphire. You can obtain 112 bar 2 gallium nitride. It is semipolar too. You don't need to trace the substrate, silicon substrate. So you can obtain. This is related to the polarity of those crystal structures, as I told you earlier.
So when you change the size of your wells or number of your wells, doesn't the emission wavelength change by a lot? Is it still blue lights? Or
Yeah,
you have to
maybe
compensate?
in the 11 bar 01 LED, you saw that we use same active region in the same conditions. However, we obtained for one semipolar, it was 450 nanometer. For the other one, it was 430 nanometer. Both are in blue. However, there is a shift because of the more indium incorporation in the semipolar direction. So both are blue. It is not green, so it has to shoot above 500 in order to get green. So, however, still we are in the safe place to obtain blue emitting lasers or LEDs.